So, welcome to the 5th week. It is on multiple integrals. So, multiple integrals 3 as per the course plan. So, here today our focus would lie on double integrals over any given domain, double integrals over non-rectangular domains, over non-rectangular domains. Suppose I have a function f defined over a domain D to R, where the domain means always it is a closed convex closed and bounded set in R2. Okay. Now, if you have this given domain D, how do you integrate? How do you make the grids and all those things that you could do for the rectangular case? The idea is to make an extension of the function. So, how do you extend the function? We would say construct a function f tilde xy such that this function coincides with fxy when xy is in the domain D and is equal to 0 when xy is not in the domain D. Not in the domain D. This little idea of creating another auxiliary function which coincides with the value of f when xy is in D and is 0 otherwise goes a long way in taking the definition that we know for the rectangular case to that of the general domain. See, what happens here is very simple. Is that if I am having a domain here in R2 which is non-rectangular, and if I have defined the function like that, then take a rectangular domain which contains D, and this is D. Here R is a superset of D, R contains D. That is a bad way of writing, of course. I should rather write as D is contained in R. So, D is contained in R. So, what we are going to harp on this very simple idea that if I integrate this function f tilde over R which contains this D, and this is exactly same as integrating over D the function fxy, because at the end when I am integrating this f tilde apart from points in D, this function value is 0. So, the integral has no effect, the integral becomes 0 in that zone. The integral actually becomes 0 in that zone. There are many ways to look at it, this is one of the ways to look at it. You can figure out other ways too, which Please understand there are many things about multiple integrals and many applications. Everything cannot be shown in this little course that we are doing. So, it's really not possible to do each and everything. So, this is exactly the idea that we are going to harp on, that if I can get a rectangular zone like this, then integral, if I integrate this over this, it is the same as this. But in our case, we are going to talk about very special classes of the domain D. We are not going to take any arbitrary domain D. The domain D for us must have a structure, and what kind of structure they would have. So, these domain Ds, we will talk about the domain D for us will have a structure. And the book calls it the elementary region, right. So, we will have three kinds of domain Ds. So, one is type 1, one is type 2, one is type 3. So, let me write down what are the three types of domains. So, we will have type 1 domain, type 2 domain, type 3 domain, which we will draw on the board what these things mean. So, here we have types of domain D. Okay. Type 1 domain is when I have given you what the domain where x lies, and I say that y lies between two functions of x when x is defined between a and b. Y lies between phi 2x and phi 1x. So, let us draw what this domain D means in this particular setting. This type 1 domain, what does this type 1 domain actually mean? The type 1 domain means so here is your x which is from A to B. And so you have function phi 1x defined like this. You can have phi 2x defined like this, but that kind of domains what we are not expecting. Here you will have an important thing to remember: with phi 1x always less than phi 2x for all x in AB. This is a restriction that we have to maintain. That is, phi 1 value can never go above phi 2 value, and that is how you create the region. It could be like this. So, this is phi 2x. So, and that creates the domain D. There are many other ways also. For example, it could be like this. Of course, it could be as bad as being like this. So, that is also domain D. Domain D of the type 1. Domain D of type 2 is, of course, you have y given to you from C to D, and x will vary from psi 1 x, psi 1 y to psi 2 y. So, x will lie between them, where psi 1 y is always less than or equal to psi 2 y for all y in CD. And type 3 domain is something that can be expressed both as type 1 and type 2. A domain which can be expressed both as type 1 and type 2. Every type 1 domain cannot be expressed as type 2 domain. A domain that can, many of the domains are type 3 domains, of course, can be expressed both as type 1 and type 2. For example, I can draw a type 2 domain which cannot be expressed as type 1. For example, I can have a type 2 domain so here is your D and here is your C. So, it is something like this. So, these two are functions of y. This is psi 1 y and this is psi 2 y. Psi 2 y. Now, note, I cannot express this as a type 2 because I cannot express these curves as function of x, because if I take an x here in between this zone, say this is my AB zone, and I can take an x here. Okay, I am just wait, I will just try to make it a bit more like this. For example, it is like this. So, now if I take an x here, so it comes up to here is the maximum value. So, if I take an x here, you see here corresponding to this particular x, there are two values of y. So, this curve cannot be expressed as a function of x. So, it cannot be made into a type 1 domain. For a type 1 domain, it has to be expressed as a function of x. We will come and show with some examples what type 1 and type, how can we handle both these domains through examples, that is much better. What is important now is to show that this iterated integral business can be still carried on in this sort of setting. And how do we start those iterated integral business? The idea is very simple. So, we are looking at this very simple definition what we wrote down, that the integral d of fxy dx dy is nothing but the integral over R. Let the rectangular region be AB and CD. So, it can be written as say AB, so R, let us now take R to be in of the form. So, whenever I am writing these kind of things, you just take R of the form AB CD, AB cross CD. So, you will always write it like this, F tilde so that's now this again this integral is again equal to integral C to D integral A to this is dy dx, because here first I integrate with respect to y. So, it is dx and then dy. Okay. Now, let me try to compute such an iterated integral. In this iterated integral, in this particular iterated integral, let me try to compute, because if I have to compute this, I have to compute this. Let me compute integral C to D f tilde xy dy. Observe that now it has just become a function of y because I fixed my x. So, when I have fixed my x, so what I have done is the following. So, here is my zone. So, let me consider a type 1 type of zone. Here is a rectangular zone. This is AB and this is CD. Now, what I have done, this is, suppose this is my phi 1x and this is my phi 2x. This is my phi 1x, phi 1 and this is my phi 2. So, I have taken a particular x. So, I have taken this particular x. Now, I am trying to integrate the function on this thing as if it is a function of one variable. Now, in this case you know that the function value will coincide with f tilde will coincide with fxy only in this part, the part which I am now marking. So, it will be only coinciding with fxy in this part. In this part, f tilde xy will coincide with fxy. Remaining part, this part, f tilde is 0. On this part also f tilde is 0. So, that is very important. You have to understand that d here is bigger than or equal to phi x, because the rectangle has to contain the whole region d. So, d value has to be bigger than the maximum value of phi x, and c value has to be lesser than or equal to the minimum value of lesser than the minimum value of psi x of phi 2. So, d has to be bigger than the maximum value of phi 2x and c has to be lesser than the minimum value of phi 1x, then only it is containing everything, then only the whole domain is getting contained in that rectangle, and because that is what we want. So, if I integrate here, I know that only on this part, the part which is cutting through the domain, that is for those y values which are lying between phi 1x and phi 2x, the function value of f tilde xy coincides with fxy, otherwise the function values are 0. So, this integral is nothing but phi 1 x to phi 2 x f of xy dy. And once you know that, then integral d now, because this is same as the r, dy is integral r of f tilde xy dx dy, that this now would be same as integral a to b integral phi 1 x, because I have computed the interior part, the C2D f tilde xy I have computed, and that is nothing but phi 2 x f xy dy dx. That can be done in the other way too. If you can write it as a type 2 zone, I could switch it and write this as a to b integral C2D integral psi 1 y to psi 2 y f x y dy dx. That can also be done. So, if you write it as a type 2 zone, we will do it in the different way. We will use the iterated integral in the different way, right. Why you should try both the ways? If you get suppose you have a type 3 region where you can express it both as type 1 and type 2, what happens sometimes that if you take it as a type 2 region, type 1 region, it is difficult to compute the integral, but if you take it as a type 1 region, it becomes a type 2 region, it becomes easier to compute the integral. That is the kind of thing that might just happen. So, summarizing what we have we write, if D, the domain D is of type 1, we have integral D. See, this iterated integral story is being actually exploited very much here. So, it is of type 1 integral a to b integral phi 1 x phi 2 x f x y dy to dx. If D is of type 2, so if D is of type 2, then integral D f of x y dx dy must be of this form. Now, you have to change the role of x and y. So, it will become C to D integral psi 1 y to psi 2 y, not phi 2 but psi 2 y f of x y dx dy. This is the way you compute it. Now, if D is of type 3, whatever anything is applicable, you have to choose the way you want, which is easier. If D is of type 3, then any method is applicable. Okay. So, this is how we have defined the integral over the domain when you have this very specialized form of the domain. Okay. So, let us look at a case where the region is actually of both types. So, first example will be at a case where the region is of both types. So, for this example computation, let us first we will just use the black pen. Doing math in black is pretty interesting. So, integral find this. So, D is of type 1 with AB, because x has to be, x zone has to be specified, 0 to half, and phi 1 x is 0 and phi 2 x is x square. So, if you look at the zone on which you are integrating, so look at the zone on which you are integrating. Zero to half, and phi 1 x is 0, phi 1 x is 0, and this is phi 2 x equal to x square. Of course, we are maintaining that phi 2 x is always bigger than phi 1 x, the x square is anyway greater than equal to 0. So, this is my domain D. This is a type 1 domain, but later on we will see that this can also be expressed as a type 2 domain, and you can check out the answer. So, because it is a type 1 domain, I have a very straightforward thing to do, what we have learnt in the last slide. So, it is 0 to half integral 0 to x square x plus y. So, you see here, this is very important. Now, what is that? This is a type 1 domain. So, my y values are lying between phi 2 x and phi 1 x. So, for every x, the y value, so I have fixed my x. So, y is lying between 0 and that particular x square, that particular fixed x. So, you evaluate that and keep on doing it. So, do it for all the y's basically, do it for all the y's, that's the idea. So, do it for all the x's, right. So, this will give me 0 to half this works out as xy plus y square by 2 0 to x square dx. When it is 0, so when y put y is 0, is 0, y is x square, so it will become x cube here. When 0 part is gone, so I will just have to bother about putting x square here, x cube plus y square. So, it will become x4 by 2 dx. If we integrate it out, this will simply become 3 by 160 as the answer. So, is the domain D is also of type 2. The domain D in this particular case is also of type 2. The domain D in this case is also of type 2, because I can write y, because when x is equal to half, phi 2 half is 1/4. So, I can write CD this domain of y is between 0 and 1/4. Phi 1 x I can write as root y, this function which is the inverse, in this part is the inverse of x square. So, root y is equal to x, positive root. So, it is root y, and phi 2 x is half, this is half, and psi 2 x is half. So, you can try out this particular thing for this particular problem, and then we can think in bit more detail. Now, we want to show that sometimes when you have type 2, so for example you have this case. Let us draw a particular zone. I am drawing a particular zone. The region we are going to now draw is of type 1 but not of type 2. You will think why. So, in the x axis here is 0 0, here is 0 1, and here is 2 2. So, x is varying from 0 to 2, and this is the region we want to integrate on. So, y is varying also from 0 to 2. Observe here that this region D is a region of type 1, but D is not a region of type 2. D is not a region of type 2. Why? So, I have said it is not a region of type 2. Why it is not a region of type 2? Because it is a region of type 1, it is clear, because here you have a fixed x is from 0 to 2, that is clear, and y is lying between. In this particular case, the y domains are y is moving from y equal to x, which is this line, and also this line is y is equal to half x plus 1. But if you look at it from the perspective of y, now you take y as your main axis, say between 0 to 2, and you look at the domain D, then you do not find two functions binding this zone, domain D. There are, should I take these two only? I can't, because y can take value up to 2. So, y will also have value from 0 to 2. So, can I take just these two curves and talk about the domain? No, because I have to consider also this part of the curve. I have to also consider this part. So, there is a third entity coming in, not just two entities here, not just these two lines, two functions, which I can write express them as so y is equal to x to y equal to half x plus 1, which I can write as y 2 in 2y minus 2, x is 2y minus 2. So, this for me it will become x is 2y minus 2 to x equal to y. But what about this part? How will I take into the consideration this part? From, if I come from here to here, I can take I will consider up to this part. So, if I am y, if I am on the y segment, if I am coming from here to here, 0 to 2 to, so this is my 2, 0 2. When I am coming from here to here, up to here, I am considering it this domain. This domain can be thought about in terms of these two curves. But when I am coming from here to here, the domain is now have to thought of in terms of x equal to 0 and this curve. So, there are two different integration, two different regions that has to be posed. It can be done in terms of those things also. First integrate over this part and then integrate over that part. So, if you just if you want to do it in one shot, if you want to look at it as a type 2 domain, it is not a type 2 domain, because you have to bring the whole thing into two different parts. So, it is a composition of two type 2 domains, it is not just one type 2 domain. So, a type 2 domain. So, it cannot be taken as a region of type 2, where we can do the whole integration in one shot. So, here if you want to do the whole integration in one shot, you have to use the type 1 game. So, suppose you have an integral, whatever integral, say if in this example it is fxy is equal to x plus y whole square, then if you want to integrate, then you have to maintain that order of integration. So, here you see I have to maintain that thing, because I know it is not a type 2 domain, I cannot do anything, because in type this is actually composed of two different type 2 domains. So, I have to separately integrate, you can try out that. But here if I just want to integrate in one shot, I have to use the fact that it is a type 1 domain. So, I will have to go from x to half x plus 1, and that is the way I have to write it, x plus y whole square. So, dy first, integrating over y, and then dx. Okay. So, if you integrate it out, the answer will be 7 by 2. So, here we have a simple idea of how you will see there are several cases where the region is of type 2 and type 1, that is, the region is of type 3. So, it is both. So, sometimes if you would use a type 1 approach, it is hard to compute. If you use a type 2 approach, it will be easy to compute. For example, I will just mention this and end my talk. For example, if you take this integral, I want you to, so this is you are integrating in the type 1 approach. This is called a type 1 approach, where y is viewed as a function of x. If you want to integrate this root over 1 minus y square dy, so basically it is a kind of circle, and but if you want to write it in that form, it will become very tough to do it. You will, fxy is 1 root over 1 minus y square, then the whole integration becomes much more complicated, right. But if you want to do it much more simplistically, you can write it as a type 2 integral, because in this region that we are talking about is a circular zone 0 to 1, and this is y is root 1 minus x square. So, similarly, you can this can be thought about, this is a type 1 domain where phi 1 is 0 and phi 2 is 1 minus root over 1 minus x square. It is also type 2 domain where psi 1 is 0 and psi 2 is root over 1 minus y square. So, it can also be written as 0 to 1, 0 to root over 1 minus y square, root over 1 minus y square dx dy. So, if I had done just this root over 1 minus y square di into root over 1 minus y square, so this root over 1 minus y square would have given me 0 to root over 1 minus x square, this one. So, root over 1 minus y square would give me the area of the circle for the fixed x. So, area of a circle. So, this is the functional value, this is the area of the circle of radius 1. So, pi of r square, but here I am not taking up to 1, I am taking up to root over 1 minus x square. So, you cannot just simply use the area of the circle to easily integrate it. Here you have to use the formula and then put the limits of y. You have to use the formula for the y and put the limits, and that is a very complex integral, complex writing. So, what you do, you change it, because it is also a type 2 zone. So, it is type 1 with phi 1 x, when x is lying between 1 and 0, and phi 1 x is 0, phi 2 x is, it is also type 2 with y lying between 1 and 0, psi 1 x is 0, and psi 2 x is. So, if when I am using the type 2 thing, it becomes very easy. So, it is in terms of dx, so this is constant. So, 0 to 1 root over 1 minus y square x equal to 0 to x is equal to root over 1 minus y square. This is not the case if I use this formulation. If I just integrate over y, try to integrate this function in terms of y. This whole thing now into dy. So, this is just gives me 0 to 1, this is also root 1 minus y square, so it becomes just 1 minus y square dy, and this integral is very simple, I do not have to tell you, the answer is 2/3. So, you see that a region which is both of type 1 and type 2, this region D, the one we have drawn, this is both type 1. So, these are type 3 basically, both type 1 and type 2. So, type 1 because of this, type 2 because of, you can represent it as type 1 in this form and type 2 in this form. So, what happens is that if I take it in the type 2 form, I can do the integral much more easily. So, when you have type 3 region, you have to be very careful about which way the integral can be easily done. So, with this I end my talk here, and in the next class we are going to talk about triple integrals. Okay. Thank you very much and see you tomorrow.